Hello guys, let me start today's class. In the previous class, we talked about the basic concept of virtual memory, introducing address space and address translation. I said all processes should utilize a virtual address value to access the physical memory region. And using the MMU hardware, the operating system should be able to translate the virtual address value to physical address value. This is the address translation. In addition, we assume the entire address space of each process will be placed onto physical memory in a contiguous manner. But due to this contiguous placement, we can face one critical problem related to memory inefficiency. In today's class, I will introduce the inefficiency problem first, and we will talk about a solution to address that problem, which is called segmentation. More specifically, in this lecture, we will first understand what segmentation is and how it translates address values. And then we will look at some other important issues like memory sharing, fragmentation problem, and something like that. In our last lecture, we learned about the base and bound approach. It was a good start, but it has some big problems. Look at the figure of this address space. As you can see, there is a large chunk of free space between the heap and the stack. With the simple base and bounds method, this entire space, including the unused part, must be loaded into physical memory. So this is very wasteful. Also, this approach is not flexible. When using the base and bound approach, the operating system must find a contiguous region in physical memory large enough to hold the entire address space. However, such contiguous space can be difficult to find. So if the operating system fails to find one, the program cannot be executed. So this limitation implies that the base and bounds approach lacks flexibility. So we need a more flexible method. To solve this problem, we can use a smart idea which is called segmentation. Its main idea is to divide the address space into several logical parts, which are called segments. And each segment is just a contiguous region of memory, but it represents a logical part of the program. For example, we can have a code segment, stack segment, and heap segment. Okay, then now instead of one base and bounds pair for the entire address space, we'll have a separate base and bounds pair for each segment. And this allows us to place each segment in a different part of physical memory. Okay, then now let's take a look at how each segment is actually placed in physical memory. On the left side, we have the virtual address space of a process, and it has three segments, the program code, the heap, and the stack. So each of these segments is contiguous in the virtual address space, but when they are loaded into physical memory, they can be placed in different locations. For example, if you look at the right side, you can see that the code segment is placed starting at 32 kilobyte. The heap segment starts at 34 kilobyte, and the stack segment is placed at 28 kilobyte. So even though the virtual address space looks continuous continuous, each segment can be mapped to a different place in physical memory. This is the key idea of segmentation. And this table shows separate base and bounds registers for each segment. So by using these values, we can perform address translation for each segment. On the right bottom, we can see the formula for address translation in segmentation. To calculate the physical address, we should take the offset within the segment, which is equal to the virtual address minus the starting virtual address of the segment. And then we should add offset value to the base address of the segment in physical memory. So the formula is simple. Physical address is equal to offset value plus the base value. And this is how the MMU hardware computes the physical address for any given virtual address in segmentation. Now let's see how address translation actually works in segmentation. Here we have a simple example using the code segment. On the left side, you can see that the code segment starts at virtual address 0, and we have one instruction located at virtual address 100. So in this case, the offset of the virtual address is 100, because the offset is just the difference between the given virtual address and the starting virtual address of the segment, which is 0 in this case. Now, according to this table, the base address of the code segment in physical memory is 32 kilobyte. So to find the physical address, we simply apply the formula we just learned. That is, physical address is equal to the sum of offset and the base address. That means we should add 100 to 32 kilobyte, which is equal to 32,868. So the desired physical address for this for the target instruction is this one, right? And this is how segmentation translates virtual address to a physical address by using the offset and the base address. Now let's look at another example, but this time with the heap segment. Earlier, we saw that the physical address is computed as the sum of the offset value and the base address value. But here is something important. I mean, we cannot simply do a virtual address value plus base address value because it is not correct answer. We first need to find the offset value within the segment. Let's take the virtual address 4200 as an example. I mean, we assume a certain data is stored here at virtual address 4200. From this figure, you can see that the heap segment starts at virtual address 4 kilobyte. That is 4096 in the virtual address space. So the offset value is the difference between these two numbers. This means we can calculate the offset value by subtracting 4096 from 4200, which is equal to 104. Now if you look at the base address of the heap segment, which is 34 kilobyte in physical memory. Then we can calculate its physical address value by adding the offset value and the base address of the heap segment, which is equal to this one, right? That is, the desired physical address for this data is 34,920. In summary, you always have to compute the offset value first, not just at the low virtual address, because each segment starts at a different virtual location. Now, let's talk about what happens when a process tries to access an illegal address, that is, an address outside the segment's valid range. For example, look at this figure. As you can see, the heap segment here occupies the region from 4 kilobyte to 6 kilobyte in the virtual address space. So any address within this range is valid, but if the process tries to access 7 kilobyte, that's beyond the end of the heap segment. Then the operating system will immediately detect this as a segmentation fault. And this type of fault occurs because the MMU hardware checks every memory reference to make sure that it is within the allowed bounds of the segment. If it's out of bounds, like 7 kilobyte here, the MMU hardware raises an exception and the operating system terminates the process. That's exactly why we call this segmentation fault. Now, when it translates the virtual address to physical address, one key question arises. That is, how does the MMU hardware know which segment the address belongs to? Let's walk through this example. Suppose that we have virtual address 4200, and we can see from this figure the heap segment starts at 4096. Then we can calculate the offset value through this formula. That is, we can subtract 4096 from 4200, which is 104. Once we know the offset value, we can compute the physical address value by adding this offset value to the base address value of the segment. For the heap segment, its base address is 34 kilobyte. Then we can calculate the physical address value through this formula. That is, the desired physical address value is this one. But here is an important detail. Before completing the translation, the MMU hardware must check whether the offset value exceeds the size of the segment. If it's larger than the segment size, then it's an invalid access. Then a segmentation fault will occur. So far it's good, but there is still one question left. How does the MMU hardware even know that the address value 4200 belongs to the heap segment? To this end, one common way is using an explicit approach. That means we chop up the virtual address into two parts, like segment field and an offset field. In this example, we assume that the virtual address has a total length of 14 bits, like this figure. But why 14 bits? It's because in our example, the virtual address space is 16 kilobytes in total. And if we rewrite 16 kilobytes, it is equal to 2 to the power of 14 bytes. And at this point, The exponent part means the minimum number of bits required to express every address in this virtual address space. In other words, to uniquely identify every byte in a 16 kilobyte address space, we need 14 bits at least. Okay, then let's take a simple example. I suppose that this virtual address space is only 4 bytes in size. Okay. Okay, then how many bits would we need? The answer is just 2 bits. Because with 2 bits, we can represent 4 combinations like 0, 0, 0, 1, 1, 0, and 1, 1, right? So if the size of the virtual address space is 4 bytes, it is equal to 2 to the power of 2 bytes. And the exponent part tells us how many bits are needed to represent all possible addresses. And in this case, we need only 2 bits to represent the entire address space. Okay. And in our case, since the total virtual address space is 2 to the power of 14 bytes, right? That is 16 kilobytes. So we need 14 bits to represent all possible virtual addresses. This is the reason why the length of virtual address is 14 bits in this case. And out of the 14 bits in our virtual address, 2 bits are used for segment field, and the remaining 12 bits are used for the offset field. Then why do we only need 2 bits for the segment field? Because in our example, we only have 3 segments, code, heap, and stack, right? So with 2 bits, we can represent up to 4 combinations, 0, 0, 1, 1, 0, and 1, 1, right? It is more than enough to identify our 3 segments. So in this example, segment field use only 2 bits, and the remaining 12 bits are used as the offset value. Okay. Okay, as a result, the segment field tells the MMU hardware which segment we are referring to, and the offset field tells the hardware where inside the segment the actual data is located. Okay, then let's take a look at one example. Here we assume we have the virtual address 4200, which is written in binary like this one. Then if you look at the top 2 bits, that's 0, 1. These bits indicate the segment number. Then according to this table, 0, 1 corresponds to the heap segment like this. Okay. Okay, then now the MMU hardware can easily identify this address value belongs to the heap segment, and then it can use the offset field for the address translation. Now let's see how segmentation works in actual code. Here is a simple pseudocode example that shows how the MMU hardware can determine which segment an address belongs to and how to compute the physical address. First, in line 2, we extract the top 2 bits of the 14-bit virtual address. We do that using the mask, seg mask. Seg mask is defined here. It is 3000, and it can be written in binary like this one. And then we shifted right byte 12 bits by using another mask, seg shift. Seg shift is defined as 12. Okay, then as a result, we get a small number that represents segment number. Okay, segment index number. Okay, next in line 4, we get the offset part by masking the lower 12 bits of the virtual address using another mask, offset mask. Offset mask is defined as this value, and it can be written in binary like this one. So as a result, we can acquire the offset value through this code line. Okay, then we will check whether this offset is within bounds. In other words, whether it's smaller than the size of the segment. If the offset is larger than segment's bound, we raise the protection port, or what we usually call segmentation port. Otherwise, in line 8, we compute the actual physical address by using this formula. Okay, that is, we can calculate the physical address value by adding the base address of the segment to the offset value. And finally, in line 9, we can access the data at that physical address by using this code line. So this simple logic shows the core mechanism of segmentation. That is how the CPU translates the virtual address into physical one, while also checking that the address stays within the valid range. Okay, then this time let's talk about the stack segment. As you know, the stack goes backward, meaning that it expands toward the lower addresses as more data is pushed onto it. This is the opposite direction of how the heap grows, which expands upward toward higher addresses. Because of this, the MMU hardware needs extra support to handle the stack growth properly. In particular, it must be able to check which direction its segment grows. So in the segment register, there is an additional field which indicates the growth direction. If it's set to 1, that means the segment grows in the positive direction, that is upward, like the code and heap segments. But if we set to 0, that means it grows in the negative directions, like the stack segment. So you can see that in this table, the code and heap segments have the growth positive bit set to 1 like this. But the stack segment has it set to 0 because it expands downward in memory. In this way, the MMU hardware uses this information to correctly check address validity. Now let's take a look at how the stack segment works when it goes backward. As we discussed before, the stack has a base address of 28 kilobytes, a size of 2 kilobytes, and its growth direction flag is set to 0, which means that the stack segment grows in the negative direction. And here we have a virtual address of 15 kilobytes. We assume that a certain local data is stored here at virtual address of 15 kilobytes. And if we express this value in binary, it becomes this value. And in this value, the top two bits are 1, 1, which indicate that this address belongs to the stack segment. Okay, after that, when we extract the offset part from this address value, we can get 3 kilobytes. However, because the stack goes downward, this offset doesn't mean 3 kilobyte below the base address. Instead, it means 3 kilobyte above the bottom of the stack segment. In other words, since the stack goes in the negative direction, the MMU hardware interprets this value as a negative offset value from the base. And to calculate the negative offset value, we should subtract the maximum segment size from the offset value. And given that the maximum segment size is 4 kilobytes, we can calculate the actual offset value as 3 kilobyte minus 4 kilobyte, which is equal to minus 1 kilobyte. That is, we can say this value is the correct negative offset value corresponding to this offset field. Then we can calculate the final physical address by adding the base address of the stack segment to the negative offset value, like this, through this formula. Okay, and the desired physical address value is 27 kilobytes. So this instruction can access the memory at physical address 27 kilobytes, which is still a valid location within the stack segment. Then at this point, how do we know whether this address is valid or not? It's actually quite simple. I mean, as long as the absolute value of the negative offset is smaller than the size of the stack segment, the access is considered valid. So in this example, since 1 kilobyte is smaller than the total 2 kilobyte size of the stack segment, this memory access doesn't trigger any fault. This means this address value is a valid address value. So in summary, this example shows how the MMU hardware needs extra logic to correctly handle stacks that glow downward while still detecting invalid or out of bounds accesses. Okay, then next let's talk about how segments can be shared between different processes. In some systems, code sharing is still commonly used. For example, multiple processes can share the same code segment instead of keeping separate copies. However, this is only possible if the code segment is read-only, because we don't want one process to accidentally modify the code and affect others. To make this work, the MMU hardware provides extra support. Specifically, we add protection bits to each segment. These bits define the access permissions, such as whether the segment can be read, write, written, or executed. As you can see in this table, the code segment is marked as read execute, while the heap and stack are read write. Since the code segment is read-only, it can be safely shared among multiple processes without any risk of one process modifying the code of another. And the next issue is about the granularity of segmentation. When you say coarse-grained segmentation, that means the address space is divided into only a few large segments, like a code, heap, and stack segment. This approach is simple and efficient, but it doesn't give much flexibility for memory management. On the other hand, fine-grained segmentation divides the address space into many smaller segments. This provides more flexibility for managing memory because it's part of a program like a function or data structure could have its own segment which can be placed flexibly in different memory locations. However, supporting many segments requires additional hardware help. Specifically a segment table to keep track of all segment information, which can become quite large. That is, this approach has a scalability issue. Okay, now let's talk about fragmentation, which is one of the major challenges in memory management. Here, we first look at internal fragmentation. Basically, this happens when memory is divided into fixed size blocks, and a process is assigned a block that is larger than what it actually needs. In that case, the unused portion inside the block cannot be used by other processes. That is, it's simply wasted space. Let's take a look at this figure. In this figure, you can see that its process A, B, and C is allocated a fixed size block in physical memory, like this part. But if any of these processes do not use the entire block, the remaining unused part becomes internal fragmentation, like this part. So internal fragmentation means wasted memory space inside the allocated memory block. This is the definition of internal fragmentation. Now let's move on to external fragmentation. This type of fragmentation happens when there's enough total free memory to satisfy a process request, but that free space is not contiguous. It's scattered across different locations in physical memory. So even though in total we have enough memory to fit process A in this figure, the operating system cannot handle this process because the available free blocks are separated by allocated ones, like this. As shown in the figure, process A needs 20 kilobytes of memory space. But all the free regions are broken into small pieces, and none of them are large enough to hold the process in one continuous block. So even though there is enough free space overall, the operating system still cannot allocate memory for process A. This is called external fragmentation. That is, in this situation, memory is wasted because free blocks are scattered and cannot be used effectively. Now with segmentation, we can have multiple segments per process, and each segment can have a different size depending on what it stores. So this approach greatly reduces internal fragmentation. since we no longer need to allocate fixed size blocks. However, external fragmentation can still occur because even though segmentation gives us more flexibility, we may still end up with many small holes of free space scattered across physical memory. In the example we saw earlier, there is total 24 kilobytes of free space, but since it's not one contiguous block, the operating system still cannot allocate a 20 kilobyte segment for process A. So to solve this problem, the operating system can perform compaction, which means rearrange the existing segments in physical memory so that all free space is combined into one large block. But compaction is costly because the operating system must stop running processes, copy data around, and update the segment register values accordingly. Here is a simple example of memory compaction. On the left, we can see memory before compaction. There is enough total free space to hold process A's code segment, but the free blocks are scattered, that is, they are not contiguous. So even though we have enough memory overall, the operating system cannot allocate the 20 kilobyte segment. On the other hand, on the right side, we can see the memory after compaction. That is, the operating system has rearranged the allocated segments so that all the free space is combined into one large block, like this part. Then now the operating system can easily place process A's code segment into the space. However, as mentioned before, this method is expensive because moving memory around requires stopping all processes and updating segment information. Okay, then next, let's go over some of the main advantages of segmentation. First, segmentation enables sparse allocation of address space. This means that different parts of the address space, like the stack and the heap, can grow independently without interfering with each other. It also helps reduce internal fragmentation, since each segment can be sized just as needed. Second, segmentation is fast, easy, and well suited to hardware. Address translation only requires adding the base and offset, so it's very efficient to implement. And next, segmentation makes it easy to share memory between processes. Multiple processes can share the same code segment if they use the same base and bounds. For example, shared libraries are often handled this way. And finally, segmentation supports dynamic relocation. Each segment can be independently moved around in physical memory, and only its base register needs to be updated. However, segmentation also includes several limitations. First, each segment must be allocated contiguously in physical memory. This means that a single segment has to fit into one continuous block of memory. That is, it cannot be split across multiple locations. As a result, segmentation still suffers from external fragmentation, and sometimes there might not be enough contiguous physical memory available for large segments. And second, segmentation is still not flexible enough. For example, if we have a large but sparsely used heap or contained in a single logical segment, the entire heap must still reside in memory, even the unused portions. So, although segmentation improved memory management compared to simple base and bounds methods, it still leaves room for inefficiency. So, to summarize today's lecture, we learned how segmentation provides a more structured way to manage memory by dividing a program into logical units like code, heap, and stack segments. So this approach helps reduce internal fragmentation, but we also saw that segmentation still has some challenges, mainly external fragmentation and the lack of flexibility when handling large sparsely used segments. So in a later lecture, we will discuss more advanced memory management techniques that aim to eliminate external fragmentation entirely. Okay, then that's all for today's class. Thank you for your attention, and I will see you in the next class.